The universe is a symphony of complexity, a grand orchestra where every element plays a crucial role in the cosmic performance. From the smallest atom to the largest galaxy, systems interact and evolve in a delicate balance. Each particle, each celestial body contributes to a vast network of interactions that define the very fabric of reality. This intricate dance of order relies on a fundamental principle: control. Control is the unseen conductor guiding the movements of each component, ensuring harmony and coherence in the grand scheme of things. Control mechanisms, whether subtle or overt, govern the behavior of these systems, ensuring their stability and functionality. Without control, chaos reigns. Imagine a construction site without a foreman or a city intersection without traffic lights. The result would be disorder and inefficiency. Systems break down, order dissolves, and the intricate structures of the universe crumble. The absence of control leads to catastrophic failures, as seen in natural disasters or structural collapses. Understanding control is paramount to comprehending the universe's intricate workings. It is through the study of control that we can predict, manage, and even manipulate the behavior of complex systems. It allows us to predict system behavior, mitigate risks, and even harness the power of complexity for our own purposes. For instance, weather prediction models rely on understanding atmospheric control mechanisms to forecast storms and prevent disasters. Whether we study the swirling of galaxies or the intricate machinery of a cell, the principle of control remains a constant. It is the thread that weaves through the tapestry of existence, connecting the microcosm to the macrocosm. It is the invisible hand that guides the evolution of systems, shaping the universe as we know it. From the flow of rivers carving landscapes to the meticulous design of architectural marvels, control is ever present. Control, however, is not a static concept. It is a dynamic process, constantly adapting to internal and external changes. Just as weather patterns shift and plants grow, control mechanisms must evolve to meet new challenges. It is a dynamic process, constantly adapting to internal and external changes. Systems must be able to respond to disturbances, adjust their internal mechanisms, and maintain equilibrium in the face of constant flux. This adaptability is crucial for survival and efficiency. Systems must be able to respond to disturbances, adjust their internal mechanisms, and maintain equilibrium in the face of constant flux. This dynamic nature of control is what allows systems to evolve, innovate, and ultimately persist over time. Consider a ship navigating through a storm, constantly adjusting its course to stay afloat. This dynamic nature of control is what allows systems to evolve, innovate, and ultimately persist over time. It is through this continuous adaptation that forests thrive, through seasonal changes, and cities grow and develop. The study of control in complex systems is a journey into the heart of order itself. It is an exploration of the principles that maintain balance and drive progress. Researchers across disciplines collaborate to uncover these secrets, shedding light on the mechanisms that sustain life and civilization. It is a quest to understand the fundamental principles that govern the universe, from the smallest scales to the grandest cosmic structures. By studying particle collisions in physics labs or observing the vast expanse of the Milky Way, we inch closer to grasping the essence of control. By unraveling the mysteries of control, we gain a deeper appreciation for the intricate beauty and delicate balance of the cosmos. Each discovery brings us one step closer to understanding the profound interconnectedness of all things, revealing the elegance of the universe's design. The concept of control transcends scientific disciplines. It is a fundamental principle that weaves through the very fabric of our understanding of the universe. It is woven into the very fabric of physics, dictating the behavior of both the familiar and the bizarre. From the grand scale of celestial bodies to the minute interactions of subatomic particles, control is a key player. In the macroscopic world, Newtonian physics reigns supreme. This classical framework, established by Sir Isaac Newton, provides a clear and predictable understanding of how objects move and interact. Objects move in predictable ways, governed by forces and inertia. Whether it's a car speeding down a highway or a child tossing a ball in the park, the principles of motion are consistent and reliable. Control, in this realm, often manifests as external forces acting upon objects. Consider a simple pendulum. This classic example demonstrates how gravity and tension work together to create a rhythmic swing. Gravity pulls the bob downwards while the tension in the string constrains its motion, creating a rhythmic swing. This interplay of forces is a fundamental aspect of control in the macroscopic world. This simple example illustrates a fundamental principle of control, the interplay between opposing forces. It's a dance of balance and counterbalance, a delicate equilibrium that keeps the system in motion. Engineers have long harnessed these Newtonian principles to design stable structures, from bridges to skyscrapers. By understanding and applying these principles, they create marvels of modern architecture that stand the test of time, demonstrating the practical implications of understanding control in the physical world. These structures are not just feats of engineering, but also testaments to our mastery of physical laws. However, as we delve deeper into the realm of the very small, the rules of the game change. The deterministic world of Newtonian mechanics gives way to the strange and often counterintuitive domain of quantum physics. Quantum physics takes center stage, and the deterministic world of Newtonian mechanics gives way to uncertainty and probability waves. Here, particles behave in ways that defy our classical intuitions. Here, control takes on a more subtle form. Instead of directly manipulating objects, we influence their probabilities. This shift in perspective opens up a new realm of possibilities and challenges. Instead of directly manipulating objects, we influence their probabilities. This probabilistic nature of quantum mechanics means that we can only predict the likelihood of an event, not its certainty. Take, for instance, the behavior of electrons within an atom. Their movements are not precisely defined, but rather exist as a cloud of probabilities. This cloud represents the various positions the electron might occupy. Their movements are not precisely defined, but rather exist as a cloud of probabilities. By manipulating the energy levels within the atom, we can nudge these probabilities, encouraging the electron to occupy specific energy states. By manipulating the energy levels within the atom, we can nudge these probabilities, encouraging the electron to occupy specific energy states. This subtle form of control is the foundation for technologies like lasers and transistors. This subtle form of control is the foundation for technologies like lasers and transistors, demonstrating the profound impact of quantum control on our technological progress. These advancements have revolutionized our world, from communication to medicine, demonstrating the profound impact of quantum control on our technological progress. Control, in both its classical and quantum manifestations, is fundamental to our understanding of the physical universe. Control, in both its classical and quantum manifestations, is fundamental to our understanding of the physical universe. It allows us to make sense of the predictable and the uncertain, the macroscopic and the microscopic. It allows us to make sense of the predictable and the uncertain, the macroscopic and the microscopic. By unraveling the mechanisms of control, we gain deeper insights into the fundamental laws that govern our universe. By unraveling the mechanisms of control, we gain deeper insights into the fundamental laws that govern our universe. This journey from Newton's apple to quantum quarks is a testament to human curiosity and our relentless pursuit of knowledge.